Okay, so let me minimize this window. So in the last class, we finished RSA crypto system. One more thing is left in cryptography, which is cipher. I mean, especially Caesar cipher, which is very easy thing to do. So I'll just give you one example, and that is enough for you to understand, and you can look at the problems. Though I talked about the historical aspects of it in the last class. Okay. So what we do here, we are looking at English alphabet. So we can say that A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Q, R, S, T, U, V, W, X, Y, Z or Z, depending upon you are in America or in, right? So now I'll just map it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. So everything is mapped to your friend integer modulo 26, right? So now it is easy for us. So Caesar cipher is a kind of a substitution cipher. So basically, if I am writing something in the English, right? So for each alphabet, I will substitute it with some other alphabet. So there should be a rule. One very simple rule is, suppose we shift with certain things. So for example, in place of A, suppose I write C. In place of C, I write E, like that, shifting everything, right? This is one kind of rule that is a possibility. So I can write it mathematically, something like this. F of P is equal to P plus 3 mod 26. This is a rule. So whatever is the alphabet P, I'm just shifting it by 3, right? Reducing it to modulo 26. So for example, if our text is meet you in the park. So MEET, what will be this value? 12, 4, 4, 19, 24, 14, 20, 8, 13, 19, 4, 1, 5, 0, 1, 7, 1, 0. I think you can write it down. So basically when we add 3, so now we add 3 and reduce it to modulo 26. I'm going to get 15, 7, 7, 22, 2, 3, 6, 2, 107, 1832013. So this becomes something like PHHW ERX LQ WKH SDUN. So you take it back. So we converted everything into these numbers and then reduce it to modulo 26, add 3 and reduce it to modulo 26, and then you write it down everything. You will get the numbers. Okay, so this is a very simple, this is known as Caesar cipher or substitution cipher. There has been some generalizations which I would like to mention. One of them is, and by the way, how do we get reverse? So reverse will be P minus 3 mod 26. subtract 3 from each numbers, right? And then reduce it to modulo 26, you will get back whatever you was there, In general, we have this rule f of p is equal to p plus k mod 26. So this is known as, or in the inverse of p is p minus k mod 26. This is a bit general thing, k shift. So this is known as k shift cipher. Or more general function could be ap plus b modulo 26. Something like, say, f of p is equal to 7p plus 3, right? So for example, what will be the k encode for? We can say k is 10, so f of 10 is 7 into 10 plus 3 is equal to 21 modulo 26. So this letter becomes v. So k will become v, right? So this kind of function is a more general function. Very simple thing actually. Actually, in ancient times, there were a lot of techniques, I think, which I briefly shown you. I have some of them. They were also used. They also used to have a postcard system where you make a array and make some, holes on some of the arrays. In those arrays, basically some of them are blank, and then you shift them. You write something, shift it. So that acts as a key. Then shift it, rotate it, so you get an array kind of thing written. Those kind of things were also there. Anyway, so that's something very minor thing, very simple thing, right? Probably now you can discover this very nicely. But then some of these things are easy to crack. So basically, cryptanalysis is easy. Some of them are a bit tricky. So those things, when you look at an advanced course in cryptography, you will learn more. Of course, I taught that, so lectures are available if you want to see those things anytime. Cryptanalysis of these things. How to actually. So in cryptanalysis, you try to crack the system. Okay, encrypted text is given to you, and you want to crack it. How actually you get the answer? Okay, so you want to learn that key, or especially this function. If you know the function, you know what is going on, right? That is a key thing. Anyway, so that is just a minor thing which was left. It's like starter when you go to the restaurant, right? This is the starter thing, right? So now I have to start a new topic known as logic. Normally, I teach it towards the end of the course, but I think uh, some professor asked me to teach it early. So I said, okay, fine. Not this year, last year. So I'm going in the same flow anyway. So basically, logic is something very, very uh, basic thing. And of course, if I ask you, logic is invented where? Yeah. So you know the answer. There are so many things on Indian logic and so forth. But then there are Greek philosophers who have done a lot of work. And first, I am going to talk about, so logic is of different order. They call it order 0 logic, order 1 logic, order 2 logic, order 3 logic, infinite order logic. I have never used any of these logic basically, but order 0 logic, or known as propositional logic, is quite useful in computer science. So in fact, there is a course here taught by Professor Manoj Raut, Logic in Computer Science. So it has a lot more applications, especially in the programming and other aspects. So it's something interesting. And some of this logic, some of the concepts that you study in logic are useful in, for example, in Google search. When you search a query on Google, you actually use Boolean logic or this propositional logic. No, when you go write something, so then Google actually combines it, say maybe with and keywords, like and. That's an operation. It's a logical operation, right? Or, and accordingly it searches the things. So basically, it's quite useful in Boolean searches, programming, and plenty of things. Plenty of applications. You can search yourself. But so first, I'm going to talk about propositional logic, which is really very straightforward. And the first thing is propositional logic. It's very easy to understand. So basically, proposition is a statement or a sentence, right? So something like this. Nagpur is the capital of India. So this is a statement or sentence. So is it true or false? I can say it is false, right? Very good. 2 plus 2 is equal to 3. Hmm? So if you're doing modular arithmetic, of course, what is the context? That is very, very important, right? So anyway, so sometime 2 plus 2 is equal to 3 also. Now you know, right? So that's okay. So anyway, 1 plus 1. This is 2. True, right? So these are, propositions and kind of sentence, and we can say whether it is true or false, right? But as I mentioned, there was a paradox which I mentioned in my probably first class, right? Take a statement that the sentence on the other side of the paper is true, reverse it, and write down the sentence on the other side of the paper is false. And then you are in a problem, right? You assume one thing to be true, and then it turns out to be false, right? So, so basically, we are not dealing with those kind of things. By the way, there are some examples. If I ask, what time is it? Is it a proposition? It is not a proposition because we cannot assign true or false, right? So those kind of things are there. So it is not a proposition. Very good. So propositional variables, we write it like small letters of English alphabet, P, Q, R, S, and so on. Okay, like that. Let me now, and truth value is either true or false. Truth value of a proposition is either true or false. That's how we denote it. So if P is a proposition, then we define negation of P. Sometime also by P bar. In some books, you'll find P bar. So that means it is not the case that P, right? So the truth table is just opposite. So let us take a very simple example. P is, today is Friday. What is the negation of P? Very good. So by the way, all this is very common sense, right? So we denote all this business by what is known as truth table, TT. P, negation of P. If this is true, then this is false. If this is false, then this is true. Right? Negation. Negation of P. Okay. So these propositional logics are very useful actually also in proving certain things. Suppose you have to prove that P implies Q. Then you can say that negation of Q implies negation of P, the same thing, right? So those kind of things are easy. So that you can actually wait क्या कर रहे हो चाय के लिए होगी ना प्रॉब्लम एक छोटी सी तो T problem. So show that P implies Q is same thing as negation of Q implies negation of P. How will you show that? Truth tables. Very good. So just make the truth table and show that. Okay. Anyway, so let me talk about few more things here. Another operation. This is known as conjunction, or AND operation for proposition P and Q, right? How it works? P, Q, and this is also known P meet Q. They also call it P meet Q, P conjunction Q, all different names are there, right? Or P and Q. If this is true, then this is true. This is true, this is false, and this is false. So it's like AND operation, right? You know this, very common. And I think set theory is also an example where you can see some of these things very common, right? Third operation, P join Q or P or Q. This is also known as disjunction. So truth table is P, Q. This is true, then this is true. This is true, this is false, and this is true. This is false, this is true, then this is true. If both are false, then this is false. Okay. This is also very easy. OR operation. Or I think in set theory you might have A union B, right? Third one, which you are very familiar, is exclusive OR. Exclusive OR, or we call it as P exclusive OR Q operation. True, true, false. 1 plus 1 is equal to 0, right? You know that. True, false, true, false, true, true, false, false. So these are 4 of them are very easy thing. Now I am going to look at some more complex propositions, right? Or kind of connections between them. So we can now come to what is known as conditional statement. Conditional statement. So if P is the proposition, will imply Q. P will imply Q, right? So that means if P, then Q. So P is kind of hypothesis, Q is kind of conclusion, right? Now this is false, so I should say look at the truth table. True, 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 right? Fine. This is true, this is false, 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 true, true, and false, false. So there are different ways you can say that if P then Q, if P comma Q, P is sufficient for Q, Q if P, Q when P, all kind of shorthands people write, right? Q is necessary for P, Q follows from P. Okay. So this is the conditional statement. Now we come to what is known as converse. Q implies P is converse of P implies Q. Conditional statement. So we say that contrapositive statement of P implies Q is negation of P implies negation of Q. Sorry, negation of Q implies negation of contrapositive, right? So if P implies Q, so negation of Q implies negation of P. I just told you that you need to prove this anyway. Biconditional. Biconditional statements. P if and only if Q. I think all these things you, when you are doing proofs, you know these things, you know, you use quite often these things, right? P if and only if Q. That's a biconditional proposition. The truth table is true, 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 false, 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 true, false, false, false. So now I think saw certain basic propositions and certain conditional statements, right? Now, many times you want to show equivalence of certain things, right? Some expression is given and another expression is given. You want to show them they are equivalent. So how do you do that? You just make the truth table for both of them and see they are the same, right? Their final values are same. That means both are equal. So let me show you one example. By the way, before that, I want to look at compound propositions. So example is P join negation of Q implies P. This is a compound proposition. You can make a table. PQ negation of Q, then P join negation of Q, need Q, then we have P join negation of Q implies P. So you start with PQ. when both P and Q are true, I know negation of Q will be false. This will be true. Just using the previous results, right? This will be true. This finally this will be true. This is true. This is false. This is true. This is true. This is false. This is false. False, true, false, 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 true, false, false, true, true, false. So just easy. You can fill this, right? Based on the basic things, you know what is P. So this you vary for P and Q, true and false, all possibilities, and then calculate everything as usual, right? On the previous results. So we arrive at this value. Okay, it's an example of a compound proposition. By the way, when we have some sort of expression, of course, there should be an order. Which one I should evaluate first? Okay, so that I can make a table. Precedence of logical operations. So operator and precedence. This one negation is the first. Meet is second. Join is third. Implies is fourth, and biconditional if and only if is fifth. This is the order in which we evaluate the expressions. Okay. Now I will show you propositional equivalence. First of all, some definition. A compound proposition that is always true, no matter what the truth value of the propositions that occur in it. You know what is the name for this? Very good. Yes, sir. So you might have read in high school, right? So iska matlab you know logic, right? By the way, I should give you one very interesting problem. So when I was studying logic, so I came up with this problem, and I actually experimented with it. It turns out to be very useful for me. Whenever 2 or 3 people are having discussions, right? Having discussions. So you are giving some argument, somebody is giving some counter argument. How to win any argument? You know the technique? You can use logic there. Actually, you know, whenever humans are interacting with each other, you know, based on their knowledge of experience, the radius of circle of their knowledge, right? They will put an argument or counter argument. Surprisingly, I have found no matter with whom I am discussing, there are certain fixed arguments. You can always convert any discussions into certain fixed arguments. And you know, in those fixed arguments, you win. I mean, there is no counter argument. So you can always win any discussions, you know. It's very nice technique. So sometime if you want to try with me, you can try. It's something really interesting. And now, mathematically, can you prove it? That is an interesting question, you know. So can you prove it? If people are discussing, you can convert any discussion into certain fixed points for which there is no counter argument. Okay. This is just observation as a mathematician, you know, because you always want to do these things anyway. Similarly, a compound proposition that is always false is known as contradiction. Okay, and which is neither contradiction nor tautology is known as contingency. So now example is P join negation of P is tautology. P meet negation of P is a contradiction. How will you prove it? P negation of P, P join negation of P, P meet negation of P. Everything is done here with truth table. So if as long as you can make truth table, your life is easy. You can see that this is tautology, this is contradiction, right? So this is easy thing to do. Now logical equivalence. So compound propositions P and Q are logically equivalent. If P, if and only if Q is a tautology. Right? So we denote it by logically equivalent. Like this. Okay, so example we can take. They are logically equivalent. Is it correct? Do you remember anything? What is this? De Morgan. I hope I am writing it correctly. Just check. यहाँ पे लगा दूं? That is okay. So basically you can make the table, P, Q, De Morgan's law, true, 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 false, 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 true, false, true, false. True, false, true, false, false, true, false, false, true, true, false, true, false, false. Then we have false, 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 true, 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 true. So you can see that this and this are same, right? So this column false, 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 true, false, 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 true is same. So both are logically equivalent. ये सब तो बहुत आसान है, since you know already, right? So करना तो है basically. That's why the assignment that I posted is a little bit non-trivial. Maybe not very trivial. Saw the assignment too? Logic. So you will see that you solved it. Okay, good. Morgan's law. Okay. One can show that. Another example: P implies Q is logically equivalent to negation of P join Q. P Q join P join. Sorry, negation of P join Q. If you write so many things, many times I write wrong things actually. So just check. It's kind of monotonous thing for me anyway. True, true, false, true, 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 false, 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 true, 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 false, false, true, true, true. You can see that these two have same truth values, right? So they are logically equivalent. I think I can do many more examples, but there is no need. I mean, I will not do it. It's written in the notes. Anyway, I think I have not shared any notes with you, right? I will share all the notes, right? So you can see. So there are many laws, right? Identity law, distributive law, idempotent law, double negation law, means negation of P if negation is P itself, right? All those things are straightforward. Commutative law, associative law, distributive law, De Morgan's law, absorption law, negation law, so on. So I think I'm skipping all that portion, which is very easy. I hope you can do it and just read it, right? If I write it here, there is no point just repeating. Anyway, so what is the next? Next is predicate logic. Have you heard of that? Predicate logic? Propositional logic तो आसान है, high school में है. Predicate logic is not there. So what is the difference? In predicate logic, there are certain quantities known as quantifiers. Okay, they quantify certain things. Okay, so certain statement is true over certain range of values or something like that. You know, those kind of things comes into picture. Okay, so we talk about those predicate logic. That is also important one from application point of view. Suppose P of X is a statement, X is greater than 3. And I want to check whether it is true or false. So over a range of values of X, I know that for certain values it will be true, for certain values it will be false, right? So P of 4 is true, whereas P of 2 is false. Right? So essentially, we have this kind of x1, x2, xn is the value of the proposition function. Okay, P, proposition function P at the n tuple. So P is also known as n place predicate or n repredicate. Okay. what to do with this. So I need to tell you about quantifiers now, basically. Quantifiers. So quantifiers actually tells you that the expression is true for what range, right? For what range actually. So there is a universal quantifier, for example, if I say that Px is, so Px for all values x in the domain. Px for all values of x in the domain. Okay. So notation is for every x, Px. This is a quantifier for every x, Px, right? So for every x that we are writing is a quantifier. This is notation. So this is a universal quantifier. Universal quantifier. Yes. N-ry, जैसे बाइनरी होता है ना, बाइनरी, टर्नरी, n-ry. So if something like this is given and there is a value of x for which the statement is not true or false, so that is nothing but a counter example, right? You know that if there is something for which it is not true, it is a counter example. So we write it like this. So let me make a table here for you. Statement when true and when false. For every x, Px. That means Px is, when true, Px is true for every x. When false, there is an x for which Px is false. Right? If this is the statement for every x, Px, right? And the statement there exists x such that Px. So that means when true, there is an x for which Px is true. And when false, Px is false for every x. This is a kind of, so these two quantifiers for every x, Px, and there exists x, Px are interesting thing, right? This is for every x, Px. So for each member in the domain, right? And now it is saying that there is a element x for which you can decide about the truth or falsity of the statement. Okay. ये सब मैथमेटिक्स, ये क्या है, सिंबल्स की कहानी है और कुछ नहीं है, राइट? गोल गोल घुमाते रहो लोगों को. Anyway, so that is example. X plus 1 greater than x. So this is actually, I can say that for every x, Px, right? Where domain is real numbers. Do you agree? Because this will be true, right? For every real number x, this will be true. So for every x, Px, where domain is R, right? Okay. Second example, px, x greater than 3. What is the truth value of the quantifier? There exists x, px. Domain is R. So this is true. Right? Other quantifiers, there exist unique x, px. Or there exist remember I have used this symbol many times and it is coming from this logic. They made the symbol, so I'm using it, right? So there exists a unique x for which it is true, right? There exists a unique x for which it is true. Now, again, precedence is very important here now. So for every and there exist have higher precedence. Than all logical operations. For example, for every x, px, qx. So it's a disjunction of for every x, px and qx, right? So this is actually for every x, px, join qx. This is okay, but this is not equal to for every x, px. You understand the point? This is okay because this is a higher precedence, right? And this is not correct. Right? So now, as we talked about logical equivalence of propositional, the statements, right? Or we can also talk about logical equivalence of quantifiers. When there are quantifiers, how do we do the same thing, right? So let me mention it. Equivalence of quantifiers. I mean, involving quantifiers, I would say. So I should mention this statement. Actually, I will write it down because this is an important thing. So statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value no matter which predicate are substituted into these statements. I'm just writing because this is important thing anyway, otherwise, I could have mentioned it. And which domain of is use. So we write it like S equivalent to T. Let me give you an example. I think it will make clear. Okay. And I think this is the last. Okay. So this is the last example. So after that, I think we are done. छोटा सा example है, then you can enjoy after that, right? So statements involving predicates in quantifiers are logically equivalent if and only if they have the same truth values, no matter which predicate are substituted into the statement and which domain is used, right? So let me. Okay. So let me give you an example now. For every x, px meet qx is equivalent to, for every x, px meet qx is equivalent to, for every x, px, for every x, qx. I have to show that these two statements are equivalent, logically equivalent. Okay. So you need to see carefully. I can assume some domain D in which we are working. Okay, some domain D. Suppose for every x, px meet qx is true. This implies that if A is in a domain, some domain, I am not worrying about which domain. I can call it D if you want, right? PA meet QA is true, right? This implies that PA is true and QA is true. And this is true for every A and D, right? PA is true and QA is true for every A and D. This implies that for every x, px, and for every x, qx is true. That means we got the right hand side, right? Now opposite side, suppose for every x, px, and for every x, qx is true. This implies that for every x, px is true, and for every x, qx is true. Hence, if A belongs to D, A is an element in D, we have PA is true and QA is true. Since Px and Qx are both true for every x in D, we have for every A in D, PA meet A is true. This implies that for every x, वो black box closed, मतलब proof ends, right? It's a very simple thing, just logical thinking. Even if you don't use your logic, I mean, it's a simple statement, so that you can just do some analysis. I think that's all for today. Next class, we will do a few more things in logic. So now you're ready for your assignment 2. By the way, before you go, I just want to give you some fun. What is the next term? First term, second term, third term, fourth term, fifth term. What is the next term? So you can enjoy on your tea. Huh? What? Tell. 1 3 2 1 1 2. Actually, this is not the correct. It will be. This is your logic is okay, but it's still not correct. You see, you are using maybe predicate logic or what, I don't know. So it is 2 1 2 1 1 2 1 3. Then next, you know how it is coming? 1. How many ones? 1 1. Then how many ones? 2 ones. How many ones and how many twos? 1 1 and 1 2. Then 3 1 1 2 and so on. I mean, you can use some logic. I have used this logic that I am writing first 1, then 2, then 3. Then if you keep on doing this, beauty comes after some time. Number is fixed. You see, after that number doesn't change. You start with 2, you start with 3, you start with 4. This happens. This is known as audioactive chemistry. Okay.